Hello everyone, welcome back to Clear Creek Solutions hydrology education videos. Today we're going to be going over irrigation and water-soil relationships as it relates to stormwater design, water resources engineering, and hydrology. So we're going to get into the video right here. We have an entire playlist on our YouTube channel covering hydrology education, covering different hydrology softwares and topics. So you're going to like and subscribe to the channel and view those playlists if you want more information on hydrology. Now let's get to an introduction here. So irrigation is the application of water to soil to supplement deficient rainfall to provide moisture for plant growth. The first use of irrigation we find was by primitive man is lost in the shadows of time, but some of the works in the Nile Valley built around 3000 BC still play an important part of Egyptian agriculture to this day. The first irrigation on the American continent antedates the coming of settlers. During the 19th century, the construction of large projects in India, Egypt, Pakistan, and the United States increased the world's irrigated area from 20 to 100 million acres. So we can see here in the picture, this is an example of irrigation being utilized in Egypt in the Nile River to help deliver that precious water to plants, soils, and crops to provide food and other resources. So let's talk about land classification. The first step in planning an irrigation project is to establish the capability of the land to produce crops that provide adequate returns on the investment in irrigation works. Arable land is land that, when properly prepared for agriculture, will have a sufficient yield to justify its development. Irrigable land is arable land for which water supply is available. To be suitable for irrigation farming, the soil must be readily penetrable by water. The infiltration rate should be low enough, however, to avoid excessive loss of water by percolation below the root zone. The soil must be deep enough to allow root development and permit drainage. It must be free of black alkali, a sodium-saturated condition, and free of salts not susceptible to removal by leaching. Finally, the soil must have an adequate supply of plant nutrients and be free of toxic elements. Land slopes should be that excessive erosion will not occur. Steep slopes are conducive to water losses by surface runoff unless the soil is quite permeable. Land on the moderate slopes with an irregular surface may be leveled if the soil is sufficiently thick. Where the soil is thin, the leveling operation may remove productive soil and leave areas of relatively barren soil at the surface. Impervious substrata may lead to a perched water table, which, if close to the surface, may require expensive drainage facilities. Removal of excess water from the root zone is essential to avoid accumulation of salts and permit the aeration required by most plants. Lands located in depressions of valley floors may present drainage problems because of the lack of natural drainage outlets. The land should be located that irrigation is possible without excessive pumping or transmission costs. The general layout and size of the area should be conducive to division into field units that permit effective farming practices. The land should be adaptable to more than one crop, since changing economic or technologic factors may force changing in cropping practices. A year-round frost-free climate permits double or triple cropping and correspondingly greater return. A short growing season limits the return in the types of crops that can be grown. Soil types. Soils have been classified for agriculture purposes by the USDA, according to the relative proportion of the basic constituents of soil: sand, silt, and clay. A sandy loam is an ideal soil for irrigation because it possesses a good balance between ability to convey water and ability to retain water. Sand is too permeable and will not retain enough water, while silts and clays are too tight, their permeability is too low. You can see this in demonstration when you're on a beach, for example, how permeable sand is. But for example, if you're on a clay layer, you can see that water is basically unable to infiltrate into clay. So what about soil-water relationships? Water applied during irrigation enters the soil, and plants in turn extract water from the soil for their growth. The soil is actually a reservoir in which water is stored for use by plants between irrigation. The storage and movement of the soil water are important factors in irrigation planning. Water may be present in the zone of aeration in three different conditions. It may be moving in the large soil pores under the influence of gravity. It may be under the action of capillarity in small pore space, or it may be retained about individual soil particles by molecular attraction. The capillary water can be removed from the soil only by applying a force sufficient to overcome the capillary forces, while hygroscopic moisture can be removed only by heating. This division of soil moisture into three classes might lead one to expect a sharp discontinuity in moisture retention as each class is depleted. If the moisture content of a soil sample is measured after equilibrium has been reached under various negative pressures, a curve of moisture content versus negative pressure applied is a smooth curve. This reflects the wide range of pore sizes in the soil and indicates a gradual transition and the magnitude of the moisture holding forces in soil. Such a curve can also be established by measuring the equilibrium moisture in the soil at various levels above a free water surface. The height above the free water surface is a measure of the capillary tension existing in that soil. Curves show that a greater effort is necessary to remove each successive increment of soil moisture as the amount of residual moisture is depleted. Certain critical points on the curve have been defined arbitrarily to aid in describing soil water characteristics. The field capacity is the moisture content of the soil after free drainage has removed most of the gravity water. So we can see here in this soil relationship curve, we can see the permanent wilting point, the field capacity, and drying when compared to the soil and water relationship. Since drainage of water will continue for some time after soil is saturated, field capacity must be defined in terms of a specified drainage period, usually 2 or 3 days. A more precise definition of field capacity is desirable, and a promising approach seems to be a relation in terms of definite tension. The other end of the moisture scale from the agricultural viewpoint is the permanent wilting point. This represents the moisture content at which plants can no longer extract sufficient water from the soil for growth. The wilting point has been determined for many years by testing soil samples with young plants, and recent studies indicate that the wilting point is closely indicated by the moisture retained against a tension of 15 atm. However, it varies depending on the plant and its ability to extract water. The difference between the moisture content at these levels is the available water, the soil moisture that is useful to plants. It must be emphasized that there is a wide range in the moisture characteristics of soils within each of the major classes. An efficient irrigation procedure is to apply water when the moisture content of the soil approaches the wilting point in amount sufficient to raise the soil moisture to the field capacity within the root zone. So we can see here height in inches and the moisture content in percent. We can see in the soil-filled tube of the Norfolk fine sandy loam the comparison here between the height and that moisture content in and of itself. So you can see in the moisture content, as it continues to increase, we don't see on the high end an increase in height at that point, showing the relationship between the wilting point. So the Norfolk fine sandy loam is going to grow 35 to 40 inches based on a 25%, 30% moisture content, while the Cecil clay will require a little bit of a higher moisture content to achieve that same growth height. So we hope that lesson was helpful. We have a guide called the Hydrology Terms Guide, which outlines the 3 kinds of hydrology being used today in the industry to measure runoff and to perform calculations for design facilities. So if you're interested in grabbing that guide, go to the description box down below. If you have any questions, leave it in a comment down below as well. Thank you so much for watching, and anyways, we'll see you guys next time.